Hello, everyone. This is the third in a series of lectures covering Chapter 18. Today, we'll be talking about Section 18.3, but before that, I wanted to give a brief reminder of transmission and reflection for waves. So you may recall that we talked about the waves being passed from one medium to the other. So when that does happen, what you have is a pulse traveling through, and once it reaches the interface between two mediums, such as a thinner rope connecting to a thicker rope, what will happen is that some of the pulse will transmit through, and part of it will get reflected back. Now, whether or not it gets reflected in the same phase depends on the density of the mediums. If the pulse is traveling to a denser medium, then the reflected pulse will be upside down, it will be inverted. If you're traveling towards a lighter medium, then the reflected pulse will also still be upright. Now, if the medium is a string, then the speed depends on how tense the whole setup is, as well as the density of the different mediums. But when a wave transmits, then what will happen is its speed can change depending on medium. So in this example here, where the pulse, part of it gets reflected to the lighter string, the pulse that moves through that little light string will actually move faster than the pulse that's moving through the heavier string. And the reason that is because it's a less dense string. So speed there is faster for any wave. That said, though, what will actually happen is that the transmitted pulse, despite having a lower speed, actually still has the same frequency as the incident pulse. So having the same frequency but a faster speed means that its wavelength will actually be longer than the incident pulse. One more thing to talk about is reflection, where simply a wave reaches the end of the medium and it gets reflected back. If the end is fixed, either by hand or by a wall, by some kind of hard stop at the end, then the pulse will be reflected out of phase. But if it reaches a free end, then the pulse will be reflected back in phase, just traveling in the opposite direction. So the fact that waves can reflect is useful for generating standing waves, since after all, they can be made by sending a wave, generating a reflection, and the overlap of the incident and reflected pulses can generate the wave. Now, we have two fixed stands, however. The standing waves that can be generated are very particular. So you can't have any frequency of waves, pulses generating a standing wave in a medium that's fixed at both ends. You can only have waves that would create a standing wave where its points of no displacement, its nodes of the generated standing wave, are at the ends of the string. So in this drawing here, to create a standing wave, then you need to send frequencies that will have a node right on one end here and a node on the other end. So this sets up a boundary condition then that to create a standing wave in a medium that is bounded, you need to at least have, two nodes, one on each end. So the only allowed frequencies, right, follow that criteria. And what that means for the wavelength of those particular waves, again, is that they'll have at least two nodes, one node on one end of the string and then one node on the other. And that gives rise to a particular set of wavelengths required if you want to sustain a standing wave. So any wavelength that's equal to twice the length of the string divided by an integer number, as long as the wave that's being sent through the string and getting reflected back has a wavelength like this here, then it'll create a standing wave in the string. So you note then that the longest wavelength possible would be twice the length of the string, and any wavelength after that is actually shorter and shorter. So any wave that conforms to these particular wavelength, they are called normal or natural modes. And like I said, the first one then is when you send a wave that actually has twice the length of the medium. And if you work out the frequency using the wave speed equation, then the frequency is actually going to be the speed of the wave in the medium divided by the wavelength, which in this case for the first normal mode, which is twice the length. So what that ends up looking like, this fundamental node, this first mode, is half a wavelength being wedged between the ends of the string. And since it's a standing wave, what you'll have then is a half wavelength essentially moving up and down like a skipping rope or like an eyelash, kind of moving up and down cyclically. So it's worth pointing out then that since this is a half wavelength, then there's of course a node on either end satisfying the boundary condition, and halfway through, which is actually a distance of a quarter wavelength, because remember, this whole gap here is only half the wavelength of the wave, even though it's a full length of the medium, but it's actually half a wavelength for the wave, for the pulse, which means that halfway through the medium, you're actually at a quarter of the wave, and that's where the single antinode is for the first harmonic. So this is a point of highest displacement in the cycle. So you can keep creating more harmonics. Again, you can just follow the formula, increasing n, and you'll note then that as you do so, the second harmonic is a wave with a wavelength equal to the length of the medium. So you see how an entire cycle, entire wavelength fits in the medium here. And then the third harmonic has about a wave and a half fitting in here. And you'll note that all these harmonics, again, fit the boundary condition. They all have notes in the end. But as you go up in harmonic, you are always going to have one more antinode and one more node. So you start off with two nodes and an antinode, then you have 3 and 2, then you have 4 and 3. So that also means that frequency-wise, since as you go up in harmonics, the wavelength decreases, the frequency increases, which means that the frequency of oscillation sense for each harmonic is faster than the previous one. If we're working with a physical string, then we know the wave speed depends on how tense the spring is. So you can think of a string under these fixed ends that could be a string on an instrument like a guitar. Then we can write the fundamental frequency of this string using the speed formula, and then you can always figure out the first harmonic and any harmonic after that by knowing how tense the string is, how dense it is, as well as the length. And often the normal modes are called harmonics. And if you look at the formula, right, for the harmonic frequency, the only difference between all the possible harmonic frequencies is just the integer n. So if you know the first harmonic, then you can find the next ones by just multiplying them with the number n. Now, this relationship between the normal modes, between the normal frequencies, where each one's just an integer multiple of the fundamental one, is something that's true for strings, for string instruments. All the notes that you play, all the harmonics on a guitar or a violin, all have this like integer relationship in their frequencies and their wavelengths, which creates nice harmonies, nice sounds. But for other mediums, such as the surface of a drum, the harmonics of drums are not multiples of each other that way. And as such, when multiple harmonics are in play, they're coming off a drum set, you don't really generate this nice harmony, but rather they essentially create an overlap that's essentially amounts to noise, but their purpose is to provide percussion, not necessarily a melody anyways. So if you want to create a pure standing wave, you're essentially going to have to send a series of pulses through using some kind of motor, some kind of vibrating blade. And the idea is that once you send the pulses to one end, they'll reflect back. So you'll have this constant stream of incident pulses creating reflected pulses. And with the right frequency, with the any harmonic frequency, which again, that depends on the medium. So depending on how long the string is, um, you will need to drive your motor at certain frequencies to achieve a standing wave. But if done right, then you will create a standing wave, and then you'll have a pure mode. You'll have some harmonic frequency visible. If, however, you drive your motor, you start sending pulses that don't fit the any of the modes. So if your the frequency of your pulses does not conform to this formula here, then you will not achieve a standing wave. You'll achieve a really unstable wave that doesn't have as much amplitude as the harmonics, and you won't get a nice, in the case of an instrument, then you won't get a nice loud sound. So again, you can actually determine ahead of time what frequencies will be harmonics for your string, because you can calculate the harmonic frequencies by knowing the speed of waves on that string, and also it depends on how long the string is. Worth pointing out too that as your medium, your string here, if you're using a longer medium, they'll make your fundamental frequency much smaller, so you'll be able to drive your motor at a much smaller frequency to generate a standing wave in it. So in this GIF here, again, big thanks to flipping physics, we can see the different standing waves that can be produced in this particular string being driven by motor. So the fundamental frequency here is at 15 hertz, and this being the fundamental frequency, this is the first mode, so this corresponds to a wavelength that's twice the medium. That's twice the length of the medium, right? So this is your eyelash, this is your skipping rope. So you see how this is standing wave, we're just moving up and down here. And the second fundamental frequency has a wavelength that fits entirely in the string. The third fundamental frequency has a wavelength and a half fitting inside the string. And if you're driving the motor at a frequency that's not a harmonic, so the next one will be 60, but here you set the motor to 51 hertz, then you don't get a standing wave. You get a really unstable shaking of the string. And again, note that it's hard to see here, right? Because it's mediums really don't. Their amplitude is fairly small, but you can kind of see the nodes. How the first one here, of course, only has two nodes. The one at 30 hertz has one in the middle, and the one at 45 hertz has four, about a quarter of the way through the string. But all of them again are fixed at both ends. That's why they're harmonics. So in reality, though, right, if we want to create a pure standing wave, that's hard, because you need to have some kind of motor or some kind of vibrating blade to send pulses through a string. So what happens though if we just try to plug a string? Because I mean, that's when we play guitar, when we play violin, we're not like driving pulses um, through the string so much as we're just plucking it, or we're just striking it with a bow. So when we do that, when we play a string instrument, when we pluck the string, we're not sending a single frequency series of pulses through, creating this uniform standing wave. But rather, when you pluck the string, you create a series of vibrations, and the resulting wave that's generated from you plucking that string is actually going to be a superposition of a bunch of different modes of that string. So when you actually pluck the string, you're actually generating an overlapping wave of multiple standing waves that cover, a range of harmonic frequencies. That said, though, for example, in the case of a guitar string, if you pluck a guitar string and you look at the waveform they generate, the standing wave component with the biggest amplitude, the loudest one, will be the first harmonic. So there's going to be a few harmonics present in the sound coming from you plugging a guitar string, but the most dominant component is that of the first harmonic, which also makes sense because the guitar string just fixed on both ends, so it has easier time sustaining the first harmonic than any second or third. But if you were to break down the waveform, you see that when you play a string, you still see those other few harmonics after the first. And if you hold your fingers against any of the frets on the guitar, then what you do is you're actually shortening the length of the strings, which means that your fundamental frequency will actually increase. So that's why by placing your fingers on the fretboard and moving further and further down the fretboards, down the neck of the guitar, that creates higher notes, that creates higher pitches, since you're increasing the fundamental frequency. And as such, you're going up octaves, so you're increasing you're going up by a semitone for every fret, so you're going up the scale. The same is true with the violin and the cello, right? By shortening the string, you change the note by a semitone or more. It's interesting that the effects of harmonics is also present in sound waves. So when you play a clarinet, when you blow into a clarinet, you're also producing this sound that's a mix of harmonics. And interestingly enough, the loudest harmonic component of that sound that you make is actually the second harmonic, not the first. And also, when it comes to the naming of the notes, then even though playing a note actually creates a bunch of harmonics overlapping, again, the fundamental harmonic is always the loudest one, so the note gets the name from the fundamental harmonic of the string. So when you pluck an open E string, you'll get a bunch of frequencies, but the loudest one is the frequency that corresponds to a pure E note. But again, if you really wanted to create a pure E note or A note or any note, then you'd actually have to either generate that with like a motor or some kind of like mechanical device, because otherwise you're not going to be able to like generate a pure note with just plucking strings, since that requires a very specific driving with a very specific frequency. So quick quiz here. We're setting up a standing wave with the boundary conditions fixed at both ends. And the question is, well, one of these is true, all of them are false except one. So part A says, well, number of nodes is equal to number of antinodes. It's not true. There's always one more node than an antinode. Part B says wavelength is equal to the length of the string divided by integer. That's not true. The wavelength is always equal to twice the length of the string divided by an integer. C says the frequency is equal to the number of nodes times the fundamental frequency. That's not true, because at the fundamental frequency, you have two nodes. So you can say that about antinodes. So for whatever frequency you're at, you have the same number of antinodes as you have whatever harmonic level you're at. So the third fundamental frequency has 3 antinodes, for example. And D says the shape of the string at any instance shows a symmetry over the midpoint of the string. So if you just look at the graph here, you do see the midpoint here, which would be, in this case, somewhere around 3 and 4, right here. there is a symmetry, which is not quite horizontal or vertical, but it's both. It's a vertical horizontal symmetry where the wave is a reflection here along this axis. So let me correct that. What I mean is, if I were to draw an imaginary line, a vertical line down here, down crossing through the node number 4 here, then what you'd get is a two halves, right? One half here and another half here, and each half kind of looks like the other half, but as an upside down mirror of the other. So when this part here is on top, the other one's right on the bottom. So if you were to flip one, you'd get the same image. And that's why there's a symmetry then about the midpoint of a string. And that's it for section 18.3. Hope you join me next time.